Okay, so it's right before spring break, and actually I'm taking off to Boston right after class. That's where I'm from, so I'm going to visit my relatives there. And so what I've already done is, so today we're going to do 29 and 30 actually, and I've already, at home I have a little document camera, and I made a video for chapters 31, 32, and 33. It's only 40 minutes long. Those are short chapters. So you can watch that. Those will both be posted after class today. So, and then I'll post this homework you'll be able to do. It's based on chapter 29 in the first part of 30. And then I'll post this homework down here that will be based on the rest of it. Okay? So you'll be able to do that too if you want. Now, I sent you all an email and I said that, okay, unfortunately these pre-lectures are ending just because we haven't filmed the rest of them yet. So I might get around to filming some more, but I figured now's the time to start. These are bonus exercises. So this first one is due Friday at midnight. Now, if you really need more time and you feel like this isn't enough notice, email me. I just thought it would be nice to get it out of the way before spring break, but if there's enough demand for it, I can move it to either here or here if people are really interested and feel like they need more time. So you can look it over and just shoot me an email and I can change that, but I thought it would be nice to get it out of the way first, especially because you can get help by the TAs. They'll still be in office hours Wednesday. I won't be there, but they'll be there Wednesday and Friday, and they can help you with that. All right, so any questions before we begin? And by the way, the week after this, I guess our exam's coming up on April 4th. No, April 3rd, Wednesday, April 3rd. And it will cover through chapter 37. So let's go to it. So we'll go to the document camera here. And here's where we left off on page 142. We were, even though we just have this simple regression, 1x drinks predicting 1y GPA, we've decided to go ahead and not only do it by the T and Z statistics, but by the F here, by using analysis of variance, okay? So that's what we did here, and we used this R squared, because as you can see, the sum of squares model, you see this sum of squares total is broken down into two pieces, sum of squares for the model and sum of squares for the error. Well, the model, R squared, that's like our correlation coefficient squared. It's the strength of our model. So R squared measures the strength of our model. R squared is the fraction of the SST that's explained by the model, and 1 minus R squared is the fraction that's left of the SST, which is like the variance of the y's, just multiplied by n, variability of the y's. 1 minus R squared is the fraction of the variability that's due to the errors. And you can see it kind of looks like a tautology. It's R squared plus 1 minus R squared, right, equals 1. And then you multiply through by SST, and you have R squared times SST, plus 1 minus R squared times SST is equal to 1 times SST. So that's an easy way to remember it. But, of course, that would be true of anything, not just SST. But this R squared times SST, that is the sum of squares model. That's the special relationship. R squared times SST is sum of squares model. And 1 minus R squared times SST is sum of squares error. Okay, so we saw that in a simpler way of doing this on the next page, instead of getting this F ratio, you can probably see that all we're doing here is we're taking the sum of squares model over the sum of squares total. So these SSTs cancel out, and then we're tweaking them by the degrees of freedom. So what we wind up with on the next page is R squared is this. I can show you the steps to it. Here, I'll do it out here. So this is equal to what? What I just said was, so this right over here, what is the mean? Here, I'll write it again. The mean square model over the mean square error. What is that? Well, that is SSM divided by its degrees of freedom over SSE divided by its degrees of freedom, right? That's how you get the mean square model and the mean square error. And so then what is the degrees of freedom for the model? Well, first of all, the sum of squares model we just saw is R squared times SST. And then SSM divided by its degrees of freedom. Do you remember what it is? It's the number of parameters in the model minus 1. And then SSE we just saw was 1 minus R squared times SST and divided by its degrees of freedom, which is N minus P. Okay? So as we just said before, these SSTs cancel out. And then I can multiply the numerator and the denominator by N minus P. That will cancel out the N minus P here and N minus P. And then if I multiply top and bottom by N minus T, we get R squared over 1 minus R squared times N minus P over P minus 1. And that's where we're at, okay? So this, as we saw, is a much easier way to compute. It's really just a shortcut version of what we were doing here. And of course, we'll get the same thing. I think we did it last time. If we want to do that, we could get the same thing. So we have, but first, we can do that later. First, just let's look at this R squared. Now for P equal 2 parameters, that's simple regression. There's a nice relationship between the F and the T. So let's remember, okay, so when P is equal to 2, right here, P is equal to 2 for simple regression. And there's just simple regression. And simple regression is the only time when you have one X, one predictor variable, it's the only time that you can use T or Z instead of F, or you're going to see chi-squared. So watch. So do you remember that T was R over the square root of 1 minus R squared times the square root of N minus 2? You see, when P is equal to 2, look what we get here. We get N minus 2 here and 2 minus 1. So this is right here is when P equals 2, and it's exactly the same as T squared. From, where did we do that? Back on page 137. I can show it to you quickly. Page 137 right here. See? Right there. And in fact, we did the same problem right here, the same exact problem. And here's how we figured it, right here. And you can see all we're doing when we're figuring the F is squaring this. The R squared over 1 minus R squared times N minus 2. Here, let's do it. Okay? So we can, why don't we just show how both of those work right down here. Okay, so this is saying what? That F with 1 degree of freedom in the numerator, and it doesn't matter how many are in the denominator, but 2 parameters, 1 degree of freedom, simple regression, is equal to T squared. In our case, we had 23 degrees of freedom because we had P equals 2, we had N equals 25, and we have R equals 0. What is it? R is equal to negative little r. Little r is equal to negative 0.2. Okay, so F with 23 degrees is 1 and 23 is the same thing as this. And let me just show you down here before we move on to chi-squared. So let's just do what we did before. So, so we have f with 1 and 23 is equal to t squared with 23. So what do I mean? So here we got, well, we have to do f. Or do we have it over here? We have it right there. So we have 0.958 is going to be equal to, we just saw negative 0.98 squared, within rounding error, approximately equal. It would be exact. It would be exact if that little dot means approximately equal, or I could just make it like this, like how I was before. So approximately equal. This is rounded slightly. So those two are the same. You see, f can only be positive, t can be positive or negative. And let's draw the picture that we had. Not only are these the same, but I want to show the relationship between the p-values. So on page 137, we did this. And we said this was our t. And we got negative 0.98. And we did a one-tailed t. In one tail, we found 16.86% here. Right there, which means there's 16.86% here as well. Now, what are we doing with the f? We did it on the previous page, but let's remind ourselves. So the f is only positive, and with 1 degree of freedom in the numerator, it's going to look, it's not going to start being symmetrical. It's still going to look like this, right? And we got this f of 0.958. That's our f, 0.958. And did we get the critical value? Just to show you, do you remember how we got this area here? Let's look and see. We did it last time, but just to refresh your memory, let's go to our p-value calculator and just show you. So here we are at the f distribution, and we have 1 degree of freedom in the numerator and 23 in the denominator. And our f value is 0.958. Right? Yeah. And we want to compute the p-value. Okay, so it's 33.79. That's what we got. By the way, what would be the critical value at 5%? What would it show up on the table? The critical value at 5% would be a p-value of 0.05. And now we want to compute the f statistic for that. So that would be our critical value. There's 5% to the tail, in the tail. So that 4.279 is our critical value there. Okay? Okay. So, all right, let's go over here now and let's write that down. So what we had was we had this, and we found out that our p-value, this whole thing here, all the way through here, this whole thing is, our p is equal to 33.79%. All right? And then we also found this critical value here for about 4.28 rounded. And that's f star. And that was equal to 4.279. We'll just round it up to 4.28. And what does that mean? That means that it's 5% from here on in. So obviously, we're not going to reject the null. We'd have to get beyond there to reject the null, right? Just as we'd have to get beyond something like 2 something to reject the null here. Now, what I want to show you is that the two-sided, look, if we do two-sided, we take a two-sided p-value, what's that equal to? The two-sided p-value using t is equal to what? Twice that, which is 33.72. So it's within round, it would be exact if I did it on the computer. It's just I rounded this a little bit. And that's exactly equal to this. So these are exactly the same. Not here, but without rounding. I rounded that one a bit. Okay? So that's the idea. And now, any questions on that? All right. Because basically, if you got the f, all you'd have to do is take the square root and you'd get the t. But you get the positive t. You can't get a directional because the alternative is always two-sided because you can only get positive values for an f. Whereas the advantage of the t is you can have negative or positive. All right, so it's the same as the two-sided. Now we can do the same thing with the z and the chi-squared. So let's look at that, okay? So the relationship between f and chi-square is analogous to the relationship between t and z. The f-stat yields more precise p-values for small n. They'll be a little bit bigger, but they're more conservative and they're more precise because we're taking into account that we don't know the standard deviations of the, in the population. But this difference becomes negligible as the sample size increases. Okay, and if you, a lot of people don't really know that, so I searched around the web and I saw an argument about it on Reddit and stuff. I thought that was crazy because people should know this, but so I found a site right here where it explains it and supports what I'm saying. I'll explain it later in here, and but I just wanted to have an outside source that also tells you it's true because you probably won't see it anywhere, most places. But it's a really, and we'll talk about the reason why you won't see it later. But for now, let's just focus on this. Okay, so now let's repeat the GPA versus strengths example using the chi-square instead of the f. Okay, so here's the chi-square statistic right here. See, it looks very similar. It has the r squared over the 1 minus r squared, like this, but it's not tweaked. It has just the n, not the n minus 2. So doesn't it remind you of the, you know, it doesn't adjust the n. It doesn't subtract off 2 there. Okay, so let's compute this chi-square statistics using what we have here. We have, okay, what do we have? We have n is equal to 25 and r is equal to negative 0.2. Okay, so r squared, we square that and we get 0.04. Okay, that's where we're getting that. And then 1 minus r squared is just going to be 0.96. That's exactly what we would do here. That part of it's exactly the same. But now, instead of multiplying by 23 like we did up here, we'd multiply by 25. So we're going to get something a little bigger. Okay, 104. That's what we'll get. Okay, so there, this is the chi-squared statistic. And how many degrees of freedom does it have? Well, remember it was always g, the number of groups minus 1 before, for like the number when we did the chi-square goodness of fit test was the number of groups minus 1. Well, here it's groups are like parameters. So here it's the number of parameters minus 1. All right, and we have 2 parameters in our model. So this is a chi-square with 1 degree of freedom. Okay, so p is equal to 2. And it's always 2 in simple regression. there's one intercept and one slope. Well, it's always equal to 2 in simple regression. So here, the degrees of freedom is equal to 2 minus 1, which is 1 degree of freedom. So a chi-square with 1 degree of freedom is the same as a z-squared. Let's see. Now look at the chi-square table to find the critical value at the desired significance level. Well, there's 1 degree of freedom, so, okay, this will be easy, because chi-square only has 1 set of degrees of freedom. So here's 1 degree of freedom. So the cutoff at the 5% is 3.84. All right, so that's our critical value. And what did we get? So let's compare it to what we've got. So our chi-square stat is equal to 1.04, and we're going to compare it to the critical value, which is, put a star there, and 1 degree of freedom, put it down here. We have 1 for this too. Okay, and that was equal to 3.84. So since it's less, just like here, same with the F, it was less. See how it was less, there was the critical value. Ours is less too, and way less, and so you cannot reject the null. If we wanted to use the actual p-value, calculator, we can do that and see what 1.04 is. Let's try it. So now we have to go to the chi-square, 1 degree of freedom, and we have 1.04. We want to compute our p-value, and we get 30.78 right there, 30.78. Okay, so now let's go back to the document here. We can write that in. So our actual p-value is 30. Was it 30.78? Was that what it said? Just want to make sure I didn't write it down here. 30.78%. Okay. So now, find the actual. Well, how does this compare to the p-value we got from the z-test? Well, it's going to be the same as the two-sided. So why don't we do the same thing here that we just did? Okay, so here we have that the chi-squared with 1 degree of freedom. See, it's this 1. When it's 1 degree of freedom, that means when it's simple regression. This is only going to work because you can only do the t and the z when it's simple regression. Okay, that's going to be the same as our z-squared. Okay, so here we got 1.04, and that should be the same as, whoops, 1.04. That should be the same as what we got with our, back on page 137, right here, you see how we did it. It's just the square root of the chi-squared, really. Negative 1.02. That's the same as negative 1.02 squared, and that checks out. Okay, and now let's do what we did before. So we did the z, and between negative 1.02 and positive 1.02, we got 15.39. I'm pretty sure. $15.39, yeah, and 16.86. Okay, 15.39. Okay, so this part is 15.39. Sorry, it should look smaller than that. It doesn't, but anyways. And so now, let's draw our picture here. we have this chi-squared right here. It looks like this, right? And we got the critical value at 5%. We got that. Right here is 3.84. This is chi-squared star. And here, that means this part right here is 5%. That's 5%, okay? But then ours, that's, can you read that? That says 3.84. That's what our, but what about our chi-square stat? Our chi-square stat was way up here. So at what? 1.04. So that's our chi-squared. And this right here, we said, this whole thing, including the 5%, is 30.78%. Now, how does it compare to that? Well, if I add those two together, what do I get? I get 30, don't I get 30.78? Yes. So this time it worked out. So this is, if I add these two together for the two-sided, so let's write that down, the two-sided p-value using z is equal to 30.78%. So these two are equal. Same. This and this. All right, so that's the idea. That basically you'll get the same value. You get the same. So that's the that's it in a nutshell. So basically, you have 4 test statistics. Let's skip to page 145 before we do another example. And you have, this is the idea, that you've got 4 test statistics now. The z, the chi-squared, the t, and the f, that are all testing the same thing. Okay? So you can all use them to test when you have one slope for simple regression, for one slope. Okay, p equals 2. And you can test whether that slope is 0 against the alternative that it's not 0. So when do you want to use which one? Well, for small n, you should use t and f because they give a little bit more accurate. Well, this is the same rule we followed before. And should we use z or t or their squares? Well, the squares are always positive, so they can't specify a non-directional. So they can only specify a non-directional alternative. They can't specify greater than or less than. But you could always divide your p-value by half at the end, and that would give you the non-directional. As long as you make that, remember, as long as you don't data snoop and you make that hypothesis to begin with. So, so the z and t can be positive or negative, so they can specify a direction. And here's the key. The p-value for the chi-squared is the same as the p-value for the two-tailed z-test, and the p-value for the f is the same as the two-tailed z-test. And so here they are, your statistics right here. So, so to find the p-value, you know the easiest thing to do is to use this chi-squared and then square root it to get the z, because that's just much easier than doing that. And same here. To figure, that's easier. So I think it's easiest to find chi-square and f, then square root them. Less rounding error to get z and t. To find p-value, look at either the area of one tail or both tails. So when would you do it? You'd do both tails when, you know, the alternative is not directional, and you use one tail when your alternative is either the slope is greater than 0 or the slope is less than 0. Same for this one. And then you'll just get half the p-value that you get for these. All right, any questions on that? So now we have one more example to do on this page that we skipped. So we can look at this one. And here we've been mostly predicting exams, final using people's midterms. This is that same data set, but now we're using homework. And as you can see, the correlation coefficient isn't as strong as it was. We used to get about 0.6 when we did exams with the same data set. Predicting final, now we're getting 0.4. So it's still a predictor, but not as strong. So suppose the homework averages and final scores of the 107 Stat 100 students were a random sample from a much larger class, say 2,000. Okay, so now we're going to use ANOVA to test that rho, that's the Greek for R, so that's that's R in the population, is 0. So here's your population. It would have thousands of points in the population. So this is the null, scatter plot for population. The whole population. Just to remind you what you're doing. The whole population. And what you're doing is you have homework, and here you have finals, and the null says that there's nothing in here. There's no relation. It's just random, right? So you might as well just predict somebody's average final for everybody. It doesn't really depend on their homework score. You have a completely flat line that the slope in the population, beta 1 equals 0, same as R equals 0. So that's what you have, rho, I should say, rho equals 0. That's not P. That's why I hate using, that's a rho. You probably think it's a P. Okay, that's a rho. It's the same as this, it's this. All right, and the alternative, we're just doing the double-sided, the not equal to 0. So we don't know whether it's kind of crazy to use a double-sided alternative here, to use a not equal, because do you think homework would really make you do worse on the final? Well, maybe. Maybe if it was just complete busy work and the people who did it were people who thought they were going to do poorly on the final. So they did it. So if were more conscientious about the homework if it had no benefit for you at all, which would be terrible, to give homework that had no benefit. That's what it would be. Okay, so here's our statistics, and look what we got. So we did get this. We got a positive correlation here, but the null is saying, hey, that's just due to the luck of the draw. If we did it again, it would disappear. It's just it's fitting some random noise in our data set. That's all it is. It's small and just due to the luck of the draw. So now we're going to do it. I think we should use these statistics. We can use right here. So we have R, so we can get R squared. So 0.4 squared is 0.16. And SST, do you remember what it is? It's N times the variance, N times SDY squared. Now, which is Y and which is X? The finals are Y, this is X, and this is Y, because we're predicting the final. And whatever you're predicting is Y. So we have 107, so we're going to use this, the SD for the Y's, times 10.3 squared. And I got 11. This is a big number because, it's variance. We're squaring this. Okay, and then multiplying, and then it's sum of squares, multiplying it by n, so it gets really big. So that's what goes way down here. So that's where our sum of squares total is. And now remember how we're going to get the sum of squares model. We're just going to r squared. If you can't remember, you say r squared 1 minus r squared. Okay, they add up to 1, right? That's a tautology. Now, we want one what? We want one sum of squares total. So it's multiply it all through by sum of squares total. Okay? So r squared times sum of squares total. So r squared we have right here. So we're just going to take that 0.16 and we'll multiply it by, that's the fraction of the total variation that we think is explained by the model. And then here you have 1 minus that, 0.84, times the same thing. So of course they add up, right? And when I did that out, I got 16.26. See, here's where you start introducing rounding error. See, these are going to cancel out when you do mean square model over mean square error. These will cancel out. But I'll just multiply them out for you now so you can see how to fill in this table. And so now this is 9,535.37, and of course there should sum to that. Now remember how you do the degrees of freedom. Okay, so the degrees of freedom, this is just your variance around the mean. There's just one parameter, the mean, so it's n minus 1. So this is 106. And these two have to add up. The model is easy. It's just p minus 1, right? The number of parameters minus 1. We have two parameters here, a slope and an intercept. So we've got 2 minus 1 equals 1. And here, we can figure it out. It has to be 105 because it has to add up. And this is n minus p. So that's the 107 minus 2, and that's 105. Okay, those are our degrees of freedom. So to get the mean square model, we get, that's just going to be 1816.26 divided by 1. And this will be 9,535.37 divided by 105. When I did that, I got 90.813. And when you take the square root of that, when you take the square root of the mean square error, that's, okay, well, let's do it. That's the square root of 90.813. And that I got to be 9.53. And that's another, the square root of the mean square error is equal to our tweaked, because we're dividing through by n minus 2, is our tweaked standard, our standard deviation plus, that's what I mean when I tweak it, errors, right? Whereas if we just divided through by n, we'd get the standard deviation of the errors. Remember, the standard deviation plus of the errors is going to be a little bit bigger by a factor of what here? I just divided through by 107. So I'd put 107 and n minus 2, 107 here in this case, and it would be over 105. Wait a minute, excuse me. I want to make it bigger, so I'd have to have 107 over 105. I want to make that bigger, to put that in the denominator. See, put this in the denominator. If I had, I would have had 107 in the square root of 107. Okay. So, any questions on that? Oh, I didn't get the F ratio. Sorry. So what's our F ratio? It's going to be 1816.26 divided by 90.813, and you get 20. Exactly. Okay. So you should see now 20. Can you remember that when the null is true, the F is about 1. So this is going to be way significant. Let's see. If we wanted to, it would be much easier. Let's just use, how about using R? How about, or using R squared, we could using this ratio, that F equals R squared over 1 minus R squared times N minus P over P minus 1. You'll see you'll get the same thing, and it's a lot easier. What would we get? We'd get 0.16 R squared over 0.84. We don't have to deal with multiplying and dividing the, these sum of squares totals. And then we just say times 105 over 1. And then you'll get exactly 22, because that's what we're doing there. All right, so it's the same thing. Now, so let's look up what we get by the p-value calculator. So let's do that. So we'll go to here, and we're using the F-test with, so let's go to the F. And in the numerator, we have 1 degree of freedom. In the denominator, we have 105. And we got an F value of 20. So we're going to compute the p-value. Whoa, look at that. It's virtually 0. 1, 2, 3, 4 zeros. Shoot, it's very, very tiny. Okay? That's the p-value. Let's see what the critical value would be, because it's off our chart. If we were using a chart, we'd want 5% here. And now what's the critical value? So there's the critical value, 3.932. Any questions on that? All right, so let's go back and write that down. And here we have the critical value, first of all, by the calculator. We can first say, let's say we had a table. Pretend we had a table that went up to, see, our table doesn't. Let me show you. Let's try our table. I don't think it does. Oh, here. Actually, we can go right here. We can look at this table. So right on the next page, on 147, we can look at about what? Here, it looks like it's about 4, doesn't it? You have 1 degree of freedom in the numerator, and you have 105, so it's somewhere in between there. Right in between. If we wanted to use the smaller one, we'd use that one. 4 point, so we'll just round to 4. So we could do that. That's our critical value. Why don't we use that table right there? So using the table, we get, by table, we compare RF equal to 20 to F star with 1 and 105, we're really using 60, equal to approximately equal to 4. So this is at alpha equals 0.05. Okay? So we're going to what? We're going to really reject the null. RF is really bigger. It's much, much bigger. So it's further out on the tail. So reject the null, big time. Okay, by calculator we got the p-value, the actual p-value for F equal to 20, or 1 and what was it, 105. 1 and 105 equal to 20. The actual is, oh gosh, it had 4 zeros. So if we change it to a percent, we'll have 2 zeros. And then it was 1967. Okay? that is it. So it's way less than 5%. Way less than 5%. All right, so we reject the null and conclude there's extremely strong evidence that the homework slope is not 0, that homework has predictive value for finals. That rho is not equal to 0. That's the homework slope in the population. Okay? So, what if we wanted to get t? Note, how would we get t? T would be equal to what? The square root of f, which would be equal to the square root of 20, which would be equal to 4.72. And the p-value for the two-sided t would be the same. Okay, it would be the same. For the one-sided, it would be half of that. So that's the idea. Any questions? All right. So we'll now do the same thing with the chi-squared. It's even easier. So the chi-squared with 1 degree of freedom, 2 parameters, is equal to r squared over 1 minus r squared. It's easier to remember this one times n. And so now it's 0.16 over 0.84 times 107. And you get a little bit bigger. This is it. And then if you wanted to square root it, you could get z. So now, the critical value, we can do the same thing by table. We can compare RF with 1 degree of freedom equal to 20.38 to F star, the critical value. And this we can do, excuse me, these are chi-squareds, Ellen. Sorry, guys. You know, when you go on automatic pilot, this is just becoming routine now, right? So we're at chi-squared, so we need to do the chi-squared. I realized, because I knew I could just flip to the back of the book, we just have 1 degree of freedom, so we can find it. The chi-square with 1 degree of freedom. We saw it before. Right here. 1 degree of freedom is right here. 3.84. Okay. But ours is look even bigger, so you really should go all the way, we can conclude that it's less than 0.1%, right? But if we want to do it at alpha equals 5%, all it has to be is 3.84. Okay, is greater than chi-squared equal to 1, which is 3.84 at 5%. And if you want to do it by the p-value calculator, oh, okay. Should we do it? Do you want me to do it by the p-value calculator? Does anybody care? Okay, it's going to be much less. You can do it by p-value calculator. It's going to be less, but let's just move on. It'll be even smaller than that. It'll be by p-value calculator. It will be less than. It'll be less than this one. Then the by p-value calculator, will be less than the p-value that using. That's a good point. Using f. So maybe that's really the takeaway here. So let me just write that down. So note that F and T are fat in the tails, FAT. F and T are fat in the tails compared to the, so that means, what does it mean? Tails measure p-values. F just has one tail, T has two tails, but they're fatter in them than the chi-square and the Z. So they have bigger p-values, because the p-values are the areas of the tails. P-values than their corresponding chi-squared and z-tests. P-values. Okay, and that's what I wanted to show you. It's going to be less than that if you did it. All right. I think you know what you're doing now. So we did this, and this is kind of interesting to look at because I've been getting this question by a lot of people. Why is the F ratio equal to 1? Why is the mean of the F ratio equal? Why is this? When the null is true, F has a mean of equal to 1. And by the way, chi-square has a mean equal to its degrees of freedom, p minus 1. But why does F have a mean equal to 1? So I think the key to think of it is let's look at this. So basically, it's this idea right here. You might star it. This explains why this is true. Okay? So we'll star this. So let's look at this. So the variance of the y's, okay, consists of random noise and maybe some signal, which can be fit by our model. So really we have this SST, the variability, is split into two pieces, the model and the error. The error we know is pure noise, but the model, according to the null, is noise too. There's no signal. So it's noise, and maybe we're hoping for a signal in there. Okay? So, but think of it as noise and maybe a signal. Now, under the null, when the null is true, when H naught is true, what does that mean? There is no signal because there's no slope. The slope is 0. So when the null is true, SSM is all noise too. So when the null is true, SSM is all noise, just like SSE. Okay, so now you have them, when the null is true, they're both noise. That's the whole point. And because you have no model, that's what the null says. So then when you tweak these by their degrees, when you adjust these by their degrees of freedom, they're both estimates of the variance of the y's. So we use SST to estimate the size of the noise. That tells us whether SSM could plausibly come just only from noise or whether it's too big. If it's too big, then we think there's almost certainly a signal there because it's way bigger than SSE. So, so what we do is we get two estimates of the variance of the y under the null. And so once we divide by their degrees of freedom, remember we have to divide by n minus 1 here. Once we divide by their degrees of freedom, then we'll get two estimates of the variance. And so their ratio, of course, should be 1. They're both all noise. The mean of the f-stat when the null is true is 1, since the null is that model that doesn't have any signal in it. The null is that the model has no signal. So that's how you should think about it. And think about, now why isn't the chi-squared the same? It's just because the chi-squared, we don't divide through the numerator by p minus 1. It's just we don't center it at 1. So its degrees of freedom is so its mean is at its degrees of freedom. Because as you notice, we didn't divide through by p minus 1. We just divided the denominator by n. And then we got that statistic where n ended. There's no p in there. So it's just centered at its degrees of freedom, whereas this one, the F is centered at 1. Otherwise, in the limit, they're the same. But that's why you won't see them as the same, because people think they're different because they look different. Except they look the same when p is equal to 2, but otherwise they look different. You'll see that later. All right, so I think that's the idea. And here for ANOVA, for regression, and of course G is just like, for ANOVA, the number of groups is the same as the number of parameters. Well, you know. And everything else is pretty much, what are we doing? So this, how are you going to remember it? This right here is central to all of them, okay? And you can think of that as the strength of the model over the strength of the errors. And so you'll see it here for the F and here for the chi-squared. All right. The only thing is, you see the n, the chi-squared doesn't have any p in here. And that's why it's centered at p minus 1. See how you divide? Look, when n's really large compared to p, these two are about the same. But this, let's say n was 3. So you'd have divided by 3 minus 1, 2 here, and you wouldn't do that here. All right, and so this is important. And I think that's it. So now we can do the last few chapters, 30 and 31. 30 is all I'm going to do. Oh, I'm hot. Okay. So 30. So this is kind of interesting. I think I like this part because now we're finally going to see how, remember I said way back on page, I don't know, I think it was page 8 or 9, that, let's see, I think it was actually page 6. We talked about, yeah, stratification. And I said, you need to break, when you think there's a confounder, you break up into subgroups so you can, you know, an observational data, so you can compare apples to apples. And one way to do it is by stratification. Another way to do it is by modeling. So we'll talk about modeling later in chapter 30. Well, we're at chapter 30, so we're going to talk about it. All right. So there are two ways to control for a possible confounding variable in observational data. One is stratification. We already saw that, which we looked at before on page 6. And the other is modeling. What do I mean? I'm going to add another variable, another predictor into our model. So, including a likely confounder as an independent variable, that's a predictor variable, an x variable, in regression model is one of the main uses of multiple regression. We'll explore fully later, but for now we're going to look at the very simplest case of an extra binary variable. So we are going to add we're going to do multiple regression with a quantitative x and a categorical binary x to allow for stratification. So here's a Stat 100 survey data, showed a negative correlation between the size of people's feet and how many shoes they had. It looked like the bigger your feet, the fewer shoes you buy. So is that causal? Does shoe size somehow, what's the relationship here? Is it the bigger your foot, is that somehow affecting the number of pairs of shoes you buy? Like, if shoes cost more when they were bigger, you use more material, that would be an explanation, a causal link. But maybe there's a confounder. Does anybody know what the confounder might be here? Here, let's look at this data online, you can see. So let's go to our PC, and let's look at the data program. And you're going to do this with sumo wrestlers. So on yours, so pay attention so you know how to do this. All right, so here I chose a data set. You'll choose, because this is where this data set is. And now I'm going to click on scatter plots. And I'm going to create this scatter plot with shoe size on the x and shoe number on the y. All right, and there's the same relationship. And we have this regression line, and we have a pretty strong negative correlation. But I think what's going on is that gender could be a confounder. Why? because girls have generally buy more shoes and they have smaller feet, and boys generally have larger feet and don't buy as many shoes generally. So if I try that, if I did stratification, I choose a split on gender. So you go here and select gender. There's other things, and there's the split. Now you go back here and you split the plots. And now you can see that the slope disappears. So it was really the confounder. You can see there's no shoe size within males, bigger feet, the slope's 0 pretty much, and within females, the slope's 0. There's no negative slope. In fact, there's slightly, tiny bit positive slopes. Okay, so neither negative, and look what happens when I combine the plots. You can see that girls here are coded as purple, there's more girls, and boys are coded as yellow, okay? And here's their respective slopes, and they're almost the same. So gender was the confounder. So if you look at the stats here, you can see that males had an average foot size that was bigger, 10.64 as opposed to 7.984, and they also had, they don't buy as many shoes, 6.8 as opposed to 19.74. Okay? Does that make sense? All right. The maximum for guy was 77. The maximum for a woman, we cut it off, was 100. The minimum was 2. And some guy only has 1 pair of shoes. Somebody who has 77 should donate some. Okay. There's the person with 77. Right there. Okay. And now, oh, and here's the girl with just 2 pairs of shoes and a size tiny little foot, size 4. Oh my goodness. Okay, so now let's go. Let's not get too distracted. So I want to go back to the document camera. All right, so here's a picture so you can, first of all, we see that gender's the confounder, and gender is both, boys are buying fewer shoes and they have a big shoe size. Or you could say girls are buying more shoes and they have a small shoe size, and that's what's doing it. And you know what? Here's a picture that will help, a real exaggerated picture. Okay, it's hugely exaggerated, but I just want to show you what's going on. All right, so this is shoe size, and this is the number of pairs of shoes people buy. People own. All right, so now we have the girls up here. Let's just say, pretend they all had small feet and they all had a lot of shoes. I'm just doing an exaggerated version. So that's the females. And there's no correlation, basically flat. That's what you see here. And then you have the males down here. Bigger feet, less shoes, and they're flat. But then you have this bogus overall correlation that's negative. So when you stratify, it goes away. So we suspected gender was the likely confounder, causing both females to have smaller feet and to have more shoes. So we broke, this is stratifying. We stratified. And saw the relationship disappear. Okay? Let's highlight that. Gender was the confounder. So here we stratified by gender, and these are our stratified regression equations. So these are our stratified regression equations. Okay, now another way we can get at this is by including gender in as a binary variable in the model. So now let's look how to include gender as an independent predictor, an X variable, along with shoe size in a multiple regression model that would work to separate out the effects of each. Okay, so first let's look carefully at how to interpret the slope of a binary predictor. What does that even look like? Because usually you say you can't do regression with a binary predictor, but you can. So here we have gender, and you have to code. So gender for X, All right, so that means we're going to code. I just did 0 for males and 1 for females. So this is key right here. All right, so now we're looking at here, and here's the males, and they have an average of 6.884 shoes right here, and they're coded as 0. Males are 0, so this is X right here. All right, gender. And here's, we're not dealing with shoe size, we're just looking at gender and shoe size, okay? So this is X1, but we have no X2 here. And here's for females, all right? Now, let's see. And here is our regression equation right here. So what is this saying? This is saying the predicted Y is equal to 6.884 plus 12.86X. Okay, and remember, this is the key. X is equal to 0 for males, and X is equal to 1 for females. So what does it give for males? What does this give for males? Well, you have the predicted shoe size is equal to 6.884 plus 12.86, and X is equal to 0. So that cancels out, and it just gives Y bar for males, okay? What does it give for females? 6.884 plus 12.86 times 1, and there you get 19.74, which is Y bar for females. So you can see what's happening here. That is, you go from 0 to 1, 0 to 1 on the X, you go up, the difference, you go up from 6.84 to 19.74. So you go up this distance right there is 12.86. That's what that is. All right? So you could think of this equation as what? Y bar is equal to Y hat. The prediction is equal to Y bar for males plus, what's this? The difference. You're adding the difference between the two of them. That's the difference is you go from 0 to 1. Plus, so this is Y bar for females. I'm going to have to move this over so you can. So this is Y bar for females minus Y bar for males times X. Okay? And so for males, X is equal to 0, and for females, X is equal to 1. So what if we switch the coding? What would happen then? If we switch the coding, then we'd have what? 0 would be females, and 1 would be males. So females would be 0, and males are equal to 1. So now we just have up here, we'd have, this would be 19.74, and it would be spread around that. And this would be 6.884. This would be Y bar for males. This is Y bar for females. And then we'd have a negative slope, right? We'd go over and then we'd go down. Go over 1 and we'd go down by the same difference, 12.86. So we'd have Y bar equals, we'd start with females are 0 here. So we'd say Y bar equals 19.74, right? Plus something times X. So when X is 0, we get females. And what are we going to put in here? Minus 12.86. So it would just be Y bar equals, if we switch the coding, whatever 0 is going to be the intercept. Whatever you code as 0 is going to be the intercept. And then the difference between the intercepts will give you the other variable. So that's the idea. So now we are going to add them both to the model. Okay, so we're going to look at, what are we going to do? We are going to predict shoe size here by 2 variables, gender, I'll code as yellow, and shoe size. Okay? So and we're going to put them in a multiple regression. So here we're going to say, all right, gender and shoe size. So, and we're going to keep the coding this way for gender. Okay? This is the shoe size one. So this is going to change for males and females. All right? And the slope of the predictor variable in the model controls for the other variables. So what does including this mean? It says if a slope for gender, what it does is estimates the difference gender makes in the predicted number of shoes owned for those with the same shoe size. So for example, males, I have a size 10, lots of men have a size 10. So we're going to say, how does it differ? Girls who have the same size foot, how much more shoes do females buy? And this is shoe size. So this says for those it controls for, so the slope for shoe size estimates how much an increase in shoe size affects the predicted number of shoes for those of the same gender. So if you just look in the males, how much is that going to make a difference? Just bigger. We saw it makes hardly any difference, basically zero difference. And among females, it makes zero difference. So that slope should drop out. It started out really big, negative. But remember, within each group, it was a tiny bit positive. So that's going to drop out. So these slopes are going to change. These slopes are going to change. So let's see what happens. So here, we did a multiple regression. And maybe I should show you how to do this, because you're going to have to do it in your homework. So let's just quickly just get the same thing up. So how are we going to do this? So we'll go back to the home. And this time, you're going to choose regression. And now you have to choose a quantitative y variable here. So in this case, it's shoe number. And then we're going to base it on gender will be our x1 and shoe size. So here we have, all right, and we're doing it as a chi-square and a z. Let's show the ANOVA table here. Is that what I have in your, let's see, the ANOVA table, yes. Okay, so this looks like the same exact thing that we have in our notes here. All right, and so let's go back to our notes. That's how I got it. And let's go back to the document camera. All right, so now let's look here. So now we're, so here, first of all, what do we have now? So we have these three parameters here. We have beta naught, beta 1, and beta 2, right? And those are our slopes. So we have three parameters here. And this is p minus 1. This is for the cut, right? What else do I need to explain here? All right, so look, very significant gender, and the shoe size is no longer significant. Remember? We saw the slope almost disappeared to 0. So the only gender is significant. Now look at the multiple regression equation for males and females. All right, so just so we don't get confused, this is this one, and this is that one. So what does the multiple regression, what does it simplify for males? Let's do males first and see if it makes sense. So for males, we have the predicted number of shoes is equal to 4.255 plus 13.51 times what? Males are equal to 0. For males, x1 is equal to 0. For females, x1 is equal to 1. Okay, so here we have 0 plus 0.2472 times x2. That's x1. So this is x1, this is x2, this is beta 1, beta b2, b2, and this is b naught. All right, so that's what we've got, and that just cancels out, and that's our equation. Now, for females, what do we have? We have y equals 4.255 plus 13.51 times 1 plus 0.2472 times how many shoes they have. So this together is 17.765. So their intercept changes. So we have the same slopes, right? Pretty much zero. It's a tiny little bit positive. But the intercept changes. See? That's the difference in their intercepts. It's not exactly like the stratified equations because they weren't exactly zero, those simple equations. All right, so that is the idea, and this is the point. And then next time, well, as soon as you want to watch it, you can see what happens when they don't have the same slope. Our next data set, we did the survey another time, and there was an interaction term. There wasn't the same slope, and then you'll see what to do there. So that's it, and have a great spring break. Hope you have a, and don't show up to class here, just watch the video. Okay? And email me, I'll be in Boston, but I'll be answering emails, so, and I can help you. So don't hesitate to email. Bye-bye.